Welcome to Learning with UNP. In this session of Data Science and Mastering Machine Learning, we are going to understand about K nearest neighbors practical implementation on a project. In here, we are going to use KNN to solve a classification problem. The objective of this project is to build a predictive model using the KNN algorithm to classify whether a person has diabetes or not. By analyzing specific features from a dataset, we will aim to determine the likelihood of diabetes diagnosis. Let me give you an overview of what exactly we will be doing in this project. In this project, we will implement the machine learning process using Python. We will load and explore a diabetes dataset, split it into training and test sets, build and train a KNN classifier, and evaluate the model's performance with appropriate metrics. We will use pandas, numpy, scikit-learn, and matplotlib for this task. Let's begin with understanding the dataset. The dataset name is Diabetes Dataset. This dataset is originally from the National Institute of Diabetes and Digestive and Kidney Diseases. The objective of the dataset is to diagnostically predict whether a patient has diabetes based on certain diagnostic measurements included in the dataset. This dataset was carefully selected with specific criteria to ensure consistency and relevance in the analysis. All instances were selected from a larger database with the following constraints. Each patient is a female of prima Indian heritage and at least 21 years old. This focused selection helps in maintaining a homogeneous sample, ensuring that the findings and predictions are particularly applicable to this specific demographic group. The constraints help in minimizing variations that could arise from different ethnic backgrounds or age groups, thereby providing more reliable and targeted insights into diabetes prediction for this population. The dataset includes independent variables like pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree function, and age. The target variable is outcome, which we will express as 1 for yes, the person has diabetes, and 0 for no, the person does not have diabetes. To begin our project, the first step is to load the diabetes dataset into our Python environment. We will use the pandas library, which is widely used for data manipulation and analysis in Python. Below are the elaborated steps and code to load the dataset. First, we will import pandas and numpy. Then, we will load the dataset from an XLSX format into pandas data frame. Finally, we will inspect the first few rows to understand the data structure and content. Here is how we import various libraries. NumPy as NP for numerical operations, Pandas as PD for data manipulation and analysis, Seaborn as SNS for statistical data visualization, Matplotlib to display, plus inline in Jupyter notebooks. Let's execute this and check. We successfully imported all the required libraries. Now, we will load the diabetes dataset into a pandas data frame using the read underscore Excel function specifying the file path. This allows us to easily manipulate and analyze the data. The code looks like this. First, we define the file path to the dataset. Next, load the dataset into a pandas data frame using the read underscore Excel function. Finally, it displays the data frame to see the loaded data. Let's execute this and check. The loaded data is here. In here, data.shape gives the number of rows and columns in the dataset data. This output indicates our data comprises 668 rows, that is instances, and 9 columns, that is attributes. These attributes include features such as glucose levels, blood pressure, BMI, and age, along with a target variable indicating diabetes presence or absence. Understanding the shape provides a quick overview of the dataset size and structure, crucial for data exploration and modeling. Before using the KNN algorithm, you may need to pre-process your data if required. This can include cleaning the data, handling missing values, and encoding categorical variables. This line of code checks for missing values in each column of the data frame data and sums them up. In this dataset, there are no missing values in any of the columns, as indicated by the output of zeros for each attribute. Let's execute this and check. As discussed, here is the output. After checking carefully, we found no missing values in our dataset, meaning all entries have all the necessary information. Also, all the data is in numbers already, so we don't need to change anything about how it's stored. This makes it easier for us to use the KNN algorithm directly without having to prepare the data first. Now, let's move on to the next step of separating features. To prepare our data for the KNN classification model, we split the dataset into two parts, features and the target variable. In our diabetes dataset, the features include medical predictors like glucose levels, BMI, and age. The target variable outcome indicates whether a person has diabetes or not. We create two variables. X contains all feature columns obtained by excluding the outcome column from the dataset. Y contains only the outcome column which serves as our target variable. This operation is crucial for training the KNN model because it allows us to provide the model with the input data X and the corresponding output labels Y separately. This way, the model learns to predict diabetes based on given medical predictors. The code is here. This line creates a new variable X that contains all the columns from the data frame except for the output column. Essentially, X now holds all feature columns such as pregnancies, glucose, blood pressure, etc. that we will use to predict whether a person has diabetes. Whereas this line creates another variable Y that specifically contains the output column from the data frame. This column represents our target variable, which indicates whether each instance in the dataset is positive 1 for diabetes or negative 0. Together, these two steps separate our dataset into X, which contains the input data, features that our machine learning model will use to learn and make predictions. Y, which contains the target data, labels that our model will learn to predict based on the features in X. Let's execute this and check. As discussed, here are the outputs. Now, let's look at train test split method. To assess our KNN classification model effectively, we use train test split from scikit-learn.model_selection to divide our dataset into four arrays: xtrain, xtest, ytrain, and ytest. Xtrain and ytrain are used for training, containing a subset of features x and corresponding target values y. X-test and Y-test are kept aside for testing, ensuring the model's performance on unseen data. The test size parameter is set to 0.3, determines the test set size 30% with the remaining data allocated for training. Random set ensures reproducible results across runs. This split allows us to train the model on one portion and validate its performance on another portion, ensuring reliability and effectiveness. The code of it is shown here. This line imports the train test split function from the sklearn.model_selection module in Python. In here, xtrain and ytrain contain 70% of the dataset used for training the KNN model. Xtest and ytest hold the remaining 30% used for evaluating the model's performance on unseen data. Test size is equal to 0.3 specifies the proportion of data allocated to the test set. Random set is equal to 46 ensures reproducibility, making the split deterministic for consistent model evaluation and comparison. Let's execute this and check. It successfully worked. Over here, let's look at model building. In the context of k nearest neighbors, KNN, there are two primary steps, KNN regressor and KNN classifier. The choice between them depends on the nature of the dataset and the goal of the analysis. In our case, since we are working with a classification dataset where the objective is to predict discrete classes, specifically whether a person has diabetes or not, we will utilize the KNN classifier. We start by importing essential libraries from sklearn.neighbors. This includes the kneighbors classifier module, which enables us to implement the KNN algorithm for classification task. This module provides functionalities for constructing the classifier, training it on our training data, predicting outcomes for new data inputs, and assessing model performance metrics. This import ensures we have access to all necessary tools to effectively build, evaluate, and analyze our KNN model. Here is the code to do so. Let's execute this and check. It successfully worked. The KNN model is set up with specific parameters, particularly n neighbors, which dictates how many neighboring data points the model will consider when making predictions. In this instance, the model is configured to utilize 25 nearest neighbors. This parameter choice significantly impacts how the model assesses similarity between data points and directly affects both the accuracy of predictions and the computational efficiency of the algorithm. The code is given here. Let's execute this and check. It is successfully executed. Once initialized, the KNN model is trained or fitted using the training data, xtrain and ytrain. This process involves the model learning from the provided data to understand relationships between features and their corresponding target outcomes. During training, the model adjusts its internal parameters by identifying patterns within the training set. This adjustment aims to enhance the model's capability to accurately predict the target variable when faced with new or unseen data points. This important step ensures the model is well prepared to make informed predictions based on the learned patterns from the training data. This is the code of it. Let's execute this and check. It's successfully executed. Once the model has been trained or fitted, it can predict outcomes for new data points. Using the testing data, xtest, the predict method applies the trained model to predict the target variable, ypred. These predictions reflect the KNN model's estimation of the outcomes for each respective input in the testing dataset. Here is the code of it. Let's execute this and check. As discussed, here is the output. The data frame mentioned here compares the predicted values ypred generated by the model with the actual values ytest from the testing dataset. By visually examining this comparison, we can evaluate how closely the KNN model's prediction match the real outcomes. This assessment provides insights into the model's accuracy and identifies areas where improvements may be needed. Such evaluation is crucial for understanding the model's performance and making informed decisions about its practical deployment. The code is mentioned here. Let's execute this and check. As discussed, here is the output. Finally, let's move on to understanding the evaluation metrics. To evaluate the model's performance, use metrics such as accuracy, confusion matrix. These metrics will help you understand how well the model is predicting the target values. First comes accuracy score. The accuracy score function from scikit-learn calculates the accuracy of our KNN classifier model by comparing predicted values ypred with actual values ytest. It quantifies the proportion of correct predictions relative to the total number of predictions made on the test dataset. This metric offers a clear assessment of the model's overall performance in accurately classifying instances into their respective classes. Here is the code of it, which yields accuracy approximately 73.63%. Let's execute this and check. As discussed, here is the accuracy. Second comes confusion matrix. The confusion matrix function from scikit-learn generates a matrix based on predicted values ypred and actual values ytest. This matrix provides a visual representation of a classification model's performance showing counts of true positives, true negatives, false positives, and false negatives. Each cell in the matrix reveals how accurately the model classified instances, offering insights into its ability to distinguish between different classes. Here is the code of it, which yields an array representing a confusion matrix. Let's execute this and check. As discussed, here is the confusion matrix. Let me explain each value clearly. True negatives. 120 instances were correctly predicted where the actual outcome was no diabetes. False positives. 10 instances were incorrectly predicted as diabetes when the actual outcome was no diabetes. False negatives. 43 instances were incorrectly predicted as no diabetes when the actual outcome was diabetes. True positives. 28 instances were correctly predicted where the actual outcome was diabetes. This matrix mentioned here provides a detailed breakdown of how well the model performed in classifying instances into their respective classes, highlighting its strengths and areas for improvement in distinguishing between different outcomes. Furthermore, to enhance interpretability, the sns.heatmap function from the Seaborn library is used to create a heat map visualization of the confusion matrix CM. This heat map displays the matrix with annotations to show the numerical values in each cell. What this part of code does is, this line creates a heat map of confusion matrix CM with annotations not is equal to true, integer formatting fmt equal to d, and a blue color scheme. CMap is equal to blues. The X tick labels and Y tick labels specify the classes no diabetes and diabetes for clarity. This line sets the title of heat map to confusion matrix. This line includes the labels of x-axis as predicted, indicating predicted classes, whereas this line includes the labels of y-axis as truth, indicating actual classes. This line displays the heat map. Let's execute this and check. Here is the heat map provided. This visualization provides a clear representation of how well the model classified instances into their actual and predicted classes, highlighting areas of correct and incorrect predictions. Lastly, the classification report function from scikit-learn generates a comprehensive report summarizing key classification metrics: precision, recall, F1 score, and support, that is, the number of occurrences of each class in y-test. Precision means the accuracy of positive predictions. Recall measures the proportion of actual positives that were correctly identified, and F1 score provides a harmonic mean of precision and recall. This report offers a detailed breakdown of the model's performance across different classes, helping to gauge its effectiveness in correctly identifying instances of diabetes and non-diabetes based on the dataset. The same is used in the code here. Let's execute this and check. As discussed, here is the classification report. Let's break down this evaluation metrics and understand it in a better way. Precision. Precision for no diabetes, class 0, 74%. Out of all instances predicted as no diabetes, 74% were correct. Precision for diabetes class 1, 74%. Out of all instances predicted as diabetes, 74% were correct. Recall. Recall for no diabetes class 0, 92%. Out of all actual instances of no diabetes, the model identified 92% correctly. Recall for diabetes class 1, 39%. Out of all actual instances of diabetes, the model identified 39% correctly. F1 score. F1 score for no diabetes class 0, 82%. A balanced metric combining precision and recall for no diabetes. F1 score for diabetes class 1, 51%. A balanced metric combining precision and recall for diabetes. Accuracy. Overall accuracy of the model, 74%. The percentage of correctly predicted cases out of the total. Macro average. The average of precision, recall, and F1 score for both the classes, treating each class equally. Weighted average. The weighted average of precision, recall, and F1 score considering the number of instances for each class. These metrics provide a comprehensive evaluation of model's performance in classifying instances into no diabetes and diabetes categories, highlighting its strengths and area that may require improvement. This is all about today's lecture. See you in the next lecture. Thank you.